Okay, look at the applications or uses of electrolysis. First, you can apply electrolysis, use electrolysis in the extraction of metals from their ore. There are metals that you can obtain or isolate from their ore using electrolysis. Example of such metal you can, from electrolysis, obtain them from their ores or compound or impurities are potassium, sodium, calcium, magnesium, and and aluminium. Okay, this metal can never occur free in nature. Potassium, sodium, calcium can never exist, or even aluminium, free like this in nature. They most likely come as compound. They exist as compound with these impurities. I'll give you an example. Something like aluminium. Yes. Aluminium exists as commonly bauxites. Bauxites. What is a bauxite? A bauxite is aluminium oxide dihydrate or hydrated aluminium oxide. Is bauxite. Now, in this bauxite, there is a little percentage of sand in it. That is silicate 2 oxide, and also hematite. That is iron 3 oxide. These are all constituents of bauxites. In the extraction of aluminium, if I want to obtain aluminium from bauxite, I will try to get rid of these 2 oxides. These oxides are they are non-amphoteric. They are not as amphoteric as aluminium oxide. So being non-amphoteric, if I dissolve this, if I react this with sodium hydroxide, if I add bauxite plus sodium hydroxide, so the aluminium oxide content in bauxite dissolve in sodium hydroxide, being amphoteric. Then the remaining oxides that are not amphoteric will float. So via filtration, these 2 oxides are filtered off from the mixture, and then what remains will be a complex sort of sodium zinc oxide. We call it sodium dioxo. Okay, we're talking about aluminium, not zinc. So it's gonna be MEAL. Okay, we're gonna have sodium dioxoaluminate 3. That is a compound formed when bauxite reacts with this. The only component of bauxite that will react with sodium hydroxide is only aluminum oxide. That's what remains. So, but by the time you add water to this, if water is added to this, we're going to have 2 hydroxide. One is sodium hydroxide, which is soluble, and aluminium hydroxide, which is insoluble. Okay. So once you have this mixture, you can get rid of this by filtration. Okay, this one will filter off, this one remains the residue. But if I want to get more of this to start to crystallize from the solution, I will produce anhydrous aluminium hydroxide. A process, we call it seeding. Okay, we seed this, to seed more of this, to increase the crystallization of this. We added dry aluminium hydroxide to this so that we can have more precipitation of aluminium hydroxide from the mixture, from the solution. Now, if that has happened, what I would not just need is to heat this precipitates to dryness. So when I heat it, I'm going to have Al2O3 plus H2O. Okay, that's what I have here. Okay, now this is anhydrous aluminum oxide, which is called alumina. The alumina is a hydroxide that has been heated at a particular temperature of 9 or 1000 degrees Celsius. That is alumina. So it's a dry aluminum hydroxide. So now, this alumina is a purified bauxite. So bauxite had to go into these processes before it can obtain alumina. So in the electrolysis of aluminium in fact, you actually extract aluminium from alumina, not even bauxite, because bauxite comes with a lot of impurities in it. So what I just need to do is to melt this, just add this in the electrolytic cell, and it will melt, but the melting point is so high. So some kind of substance is added as electrolyte to lower the melting point, which in this electrolysis, cryolite is added here to lower the melting point of aluminum oxide. So in the process, aluminum is extracted. Likewise, any of these metals are extracted by the same metal. So there are metals that you need to extract them from their ores by extraction. By electrolysis. They are potassium, sodium, calcium, magnesium, and aluminum. These are metals that are placed very high in the electrochemical series. And you have purification and refining of metal. There are metals that are not obtained directly from electrolysis. Example, copper. Okay, copper is one metal that you don't extract by electrolysis. You can extract by heating the ore. Heating the ore, fruiting the ore by any method, or by thermal, by heat, or by even reduction using some kind of reducing agents. So metal obtained from this way are not that pure. They are less than, in fact, metal obtained from here are less than 90% purified. So to purify such metals like copper in most cases, okay, in such electrolysis, it must be carried out in an electrolytic cell. Okay, so suppose I want to purify a copper. I want to purify this copper here. I want it to be purified. This is what I want to purify. What I need to do, it is impure. And this thing is impure. So since it's impure, I'm going to make this impure copper my anode. It's going to be the anode. So this is going to be my impure copper now. So this shows that it's very, very impure. It is the copper here. So this is my impure copper anode. Okay, then I have to source for a pure copper anyway, so that I'm going to handle that pure copper as my cathode. So this is going to be, so it's very cheap. So this means that copper here is pure. So this is pure copper cathode. Okay, then I must make sure the electrolytes solution used here, I must use a salt of the metal I want to purify. Preferably I'm going to use a salt electrolyte. My electrolyte is going to be a copper salt. Preferably I'm going to use copper 2 tetraoxosulfate 6 as electrolyte. Okay, during the electrolysis, so the other thing, the connection should be done here so that the cell will be complete. Okay, but is that what is not necessary? What is necessary now is you know that in purification that the impure copper should be made the anode, the pure copper should be made the what? Cathode. Then during the electrolysis, copper from the impure, because when I discussed nature of electrode, I said these two electrodes are very, very active. So since they are active, copper from this impure goes out from these plates and then go to the solution, gain an electron to form. Lose the electron to form copper 2, not gain. You lose the electron to form copper 2. And remember that when you have this copper solution, copper comes out from this plate, is coming with a lot of impurities that will be insoluble, will not dissolve very well. These are the impurities that comes alongside with the copper. Also, copper dissolved, but this is not dissolved. These impurities are now called slag. This is going to be my slag. Okay, impurities from copper. So now, that copper is mobile. This copper now is mobile. It's going to migrate again. It's going to move again out of the solution, but this time it's not going with the impurities. The impurities is not soluble, so it's not going to go with the impurities. So now copper here now is 99. Copper here now is almost 99.9% pure. But when it was here, it's about 40% pure. 40%. So now, because the impurities has left the copper. But the moment copper goes into the solution, the mass of this impure anode will never remain this size. I think it will somehow to somehow shrink. Okay, because enough copper. Look at the size before, look at the size now. So that's where the size is, because copper have gone, so there's no copper here again. Gone is the solution, then go again and meet the copper that was in the pure side. So meet the copper that is in the pure side. So you remember that the mass of copper here should also do what? Increase. So that copper that goes here, so copper goes here. So the copper you get now from this pure side is 99.9% purified. Exam focus on this. I think the examiner this year's like this kind of question was asked. And when you want to purify a copper, please take notes what the anode is, what the cathode is. The anode must be the copper you want to purify, which is impure. Okay, you hang it here, and you have to source for a pure copper, which you're going to hang at the cathode. So during the electrolysis, copper from the impure anode goes into the solution to lose electron, to form copper 2 ion with impurities which are slag. Then that same copper that move out of the plate from the anode goes to the cathode. But going to the cathode now, the copper that is purified up to 100% purified. So with this method, we use it to purify copper or metals that have not been obtained, not been extracted by electrolysis, can be purified by electrolysis. And then we look at the electroplating of objects, just like refining, electroplating also is just like refining, because both of them are carried out in an electrolytic cell. Now, that electrolytic cell for electroplating, supposing a spoon is to be electroplated, to be plated with silver, maybe a spoon that has been coated before with a tin coat or aluminium coat, but this time wants this spoon to be silver plated. Okay, I'll set up my cell as well. The cell should be set up. Okay, this is the cell. This time I want to electroplate with silver. So this side my anode will be silver anode. So here it's going to be silver anode, silver anode. This is my silver anode, silver anode. Okay, and then the cathode somehow will be something else. But I'm going to hang my spoon. The hanger that is holding the spoon. Look at the spoon here. This is the spoon. This is the spoon. This is the spoon. Okay? Or rather, this is the spoon. This is the spoon. And then this is the electrolytes. The electrolyte must be a source of the metal to be plated. So I want to plate this metal with silver. So the solution will be AgNO3. That's the electrolyte. Okay, now this is silver metal. So some silver from here, because it's active as a metal, goes in here. Okay, form Ag+. That Ag+ with the Ag+ here before will be 2 mobile. It's migrate to the spoon. Okay, when you migrate to the spoon is now at that point coated. So here is what? Silver plated or silver coated. So this is what happened here. So in this electrolysis, the electroplated objects must be made the cathode. And then the metal I want to electroplate the object with must be used as the anode. And then the electrolyte must be the source of metal you want the object to be plated with. So that is the diagram for electroplating. So you can basically improve a metal by electroplating. In production of gases, there are some gases that can be obtained by electrolysis. Such gases can be hydrogen gas, oxygen gas, or chlorine gas. You can get these 3 gases via electrolysis. Like in the electrolysis of acidified or acidulated water, hydrogen and oxygen can be obtained. using voltammeter of Hofmann's voltammeter. If I use Hofmann's voltammeter and I have acidified water, acidified water is H2SO4 in water, where I have 2H plus SO4, 2 minus H2O, we have H plus OH minus. So these two ions are very similar. So cathode will be hydrogen gas. These ions are not similar, so this one goes, so we have oxygen gas. So oxygen gas can be produced from there. I can also get chlorine gas using electrolysis. Electrolysis of concentrated NaCl, where chlorine and hydroxide will compete, but chlorine will prefer to be discharged because of concentration. So the addition of chlorine leads to the production of chlorine gases. So you can get these three gases by electrolysis. You can actually manufacture sodium hydroxide via electrolysis of this same thing again. If I'm electrolyzing conch of sodium chloride, where I have NaCl, Na plus and Cl minus, H2O, H plus, OH minus. So if hydrogen is discharged at the cathode and then chlorine is discharged at the anode, the remaining ions will recombine, because nothing is separating them, will recombine to form sodium hydroxide. So you can actually obtain sodium hydroxide via the electrolysis of concentrated sodium chloride. Thank you for watching this video, second part of electrolysis. Please don't forget, exercises on this topic is there, so you can go and see more questions from exam bodies have been asked, solved with details information. Okay, if you are new in this section, please don't also forget to hit the subscribe button to get our new uploaded video. Thank you once again for watching.